Yeah. So there's kind of four main steps for hierarchical clustering. One is to compute the distance matrix. So Jamie talked about some of those distance metrics. And then after that, what we want to do is we want to merge the clusters that are closest to one another. Then we're going to update the distance metric, and then we're going to keep doing this until there's only one cluster left. So a cluster that kind of encapsulates all of the other clusters. And Jamie already talked about the various distance metrics, right? So Euclidean distance, you can kind of think of it as the distance between point A and B in a straight line. Then there's also Manhattan distance. So you imagine that you're walking in Manhattan, going from A to B. You can't cut through buildings, but you can go down city blocks, right? So you're moving kind of perpendicularly at 90-degree angles, right? So going down and over, down and over, down and over. And the most popular one is Euclidean distance, and the one that's the default in a lot of the packages like sklearn and some of the R packages that we're going to be talking about today. I don't see Manhattan distance as much, but I also don't do a lot of clustering type of work, so it's very possible that this one is more widely used. But for today, we're just going to stick with Euclidean distance to make everything simple and make sense. So Jamie talked about all of the different linkage methods. There's one linkage method that is default in things like sklearn, and that's Ward's distance, and that's the one that we're going to use. And it's a little different in that we're looking at the sum of square error, so the within cluster error. And the idea behind this is that if we want to join two clusters that are similar, the sum of squares error is not going to increase that much. But if we join two clusters that are very dissimilar, then the sum of error is going to increase a lot. So Ward's distance looks at the within cluster error and sees how much that is increased or decreased when combining clusters together. And this one is more widely used. Again, it's default in sklearn. It is not default in the hierarchical clustering function for R. But I think that this is a pretty good one. So what I want to do is kind of walk through the steps that I just talked about and kind of show you how to apply them in R. So one important note, so when we are going to do hierarchical clustering or even k-means clustering, we need to make sure that our observations are rows and our columns are variables. We need to make sure that our variables are standardized if they're not on the same scale. Some of the packages will do this automatically for you. So you have to look at the documentation for that, and then we shouldn't have any missing data. So, use multiple imputation or listwise deletion, so there can't be any missing values. So what I have here is kind of just a basic table that we're going to use to walk through this. And then I have an explicit example that I want to walk you guys through. But the idea here is that we have observations as rows, which are just students. And then we have grades in math, music, and biology, 1 through 4. I think 1's an F and 4 is an A. Doesn't really matter for the purposes of this. But so in R, what we're going to do is we're going to take that data table or data frame and then turn it into an actual object, what we're doing here. And then we are going to take the students and assign those to the rows. And then we're going to perform a distance metric. So what we're going to do is, let's just run this in R. Here. I'm just going to run it and see if it'll output. There you go. So what we're going to do to calculate that distance matrix is we're going to use this dist function in R that takes the data frame, and then we can assign it a method. Here we're just using a Euclidean distance, but we could also put in Manhattan distance if we want. And then we call this distance matrix, we get something like this. And essentially what we're looking for here is the shortest distance. So we're going to find the lowest number in this matrix. That's 1.15. So what we're going to do now is we're going to merge those two together, and we're going to call it cluster 1, let's say. Then we're going to recalculate the distance matrix again. So here I'm just assigning a new matrix called students 2. Then we're going to turn it into a data frame, and then we're going to assign our observations to rows. And we can see here that A and B is no longer in this matrix. Now it's cluster 1, C, D, and E. Then we calculate the distance matrix again, and we get something like this. And then now we find the shortest distance in this matrix, and that is student D and E, so 1.41. So now we group those two together. So they're their own cluster now. Then we recalculate the distance matrix again. So here I'm just assigning a new matrix, make sure it's as data frame, and then I'm assigning observations to rows. So here we have cluster 1, which is A and B. We have cluster C, or student C, and then cluster 2, which is D and E. Then we calculate the distance matrix using the dist function in R, and then we get a matrix like this. Then we take the shortest distance and group those. Here would be cluster 1 and student C, and then they would be one large cluster. And then we would do this until we only have one cluster left. And that's kind of the basic idea of hierarchical clustering. But let's look at a visualization of what's going on here. So we have 6 data points here. And let's say that we find out when we calculate the distance matrix that 5 and 6 are closest. So we take that and we start drawing our dendrogram. So we link 5 and 6 together. Then we recalculate the distance matrix, and let's say we find that P2 and P3 are the closest or has the shortest distance. So then we link those two together. Then let's say that P4 is related to P5 and P6, so it has the shortest distance. Then what we can do is link P4 to P5 and P6. Then we find out that P3 is related to P2 and P1, so it has the shortest distance. So we can link P1 to P2 and P3. And then finally, we have one big giant cluster left, and that is essentially how we connect those two clusters together to get this kind of hierarchical structure. So make sense? Okay, good. So Jamie went over the dendrogram a little bit. One thing that I wanted to point out is that towards the bottom of this dendrogram, that's where most of the points are more cohesive. And as you go up the hierarchy, the clusters become more less granular. So basically there's increased separation that's going on here. So again, just know that towards the bottom of this dendrogram, those have the smallest vertical distances. And as you go up this hierarchy, those distances increase. So there's more separability where this particular cluster is different from this particular cluster. But down the lowest branches or the lowest leaves on the bottom of the dendrogram indicate how close those particular points are to one another. And again, as Jamie said, we are looking at vertical distances. We're not looking at the x-axis. Those are just arranged so it looks pretty. But what we care about is this distance on the y-axis and how far apart things are. So Jamie talked about cutting a dendrogram. And unfortunately, I cannot give any advice on how to cut a dendrogram because it is very subjective. For instance, right, if I put a cut at Y3, what we do is we look for how many of the vertical lines have been broken, and that is how many clusters we have. So here we would have 4 clusters, right? So it intersects with this line, this line, this line, and this line. But I could cut it lower. And then now we'd have even more clusters. So we'd have what, 1, 2, 3, 4, 5, 6, 7 clusters. And then if I wanted to cut it all the way down here, then we'd have even more clusters. So what I do in practice is look for the largest vertical distance and then try to cut it like the half of that distance on that vertical line. But I'm going to talk about some of the more objective ways that we can actually perform hierarchical clustering, that we don't have to play this guessing game of like, where should we cut this? And is this the right place to cut it? Most people don't do well with ambiguity, so I am one of those people. So if anything can take away the ambiguity, I'm all for it. So let's walk through hierarchical clustering in practice. So several years ago, I worked on a project with a PI and an undergrad. And for this project, what they were doing is having individuals come into the lab and free sort basically speakers or talkers. So there was like an audio file that played, and individuals had to kind of free sort the groups that these people belonged in, right? And they had talkers that had American English dialects, international English dialects, East Asian, South Asian, and Southeast Asian. And what they were trying to look at is if there is any kind of granularity in, individuals who are monolingual versus bilingual or multilingual in terms of being able to kind of differentiate those different dialects. So like if you're me who's a monolingual, I might not be able to detect some of the distinctions between those dialects, but someone else might be able to pick up like, this is this particular dialect, this is another dialect, and so forth and so on. So what we can do is we can load in our packages that we're going to use. So there's 3 packages. So Facto, Extra, and Dend Extend are for visualization of the cluster. So we can have nice, pretty hierarchical clusters. And then Easy Stats has some functions that allow us to do cluster analysis. So I'm just going to go back to R. There you go. So we can read in the data from my GitHub. Then we need to clean up the data a little bit. So there are some columns that need to be removed. We need to turn it into a data frame, and then we need to have our observations as row names. So here it's just the speaker token tag that we are putting as row names. And then we just have to get rid of the speaker column, and then we should have our data ready for hierarchical clustering. So let's run that. And let's call. So we have something like this, right? So we have our speaker token as rows, and then we have our variables on top. So, and then these are the free scores. So the first thing that we want to do is we want to calculate our distance matrix. So what we do is we feed in our clus data that we ran up here, and then we are going to use the dist function. This dot just means to feed in this particular data frame, and then we're going to use Euclidean distance, and we get a distance matrix like this. Let's see, I have a prettier version over here. So we get something that looks like this. And obviously, we're not going to do this by hand. We're not going to find the shortest distance and then recalculate everything. No, we're not going to do that. So luckily, there's a function that will do this for us, and that is the hclus function. I think you do not need to download any extra packages to run these. I think they're in the base R, but I could be mistaken. But if there is some issues, then you can find it from the stats package. But I don't think you have to download any extra libraries, but I could be mistaken. So what we do is we use this hclus function, and we input our distance matrix that we created, and then we have to choose a method that we want to use. So the wards distance that I talked about, if you want to use that, you have to use this ward.d2. There's also just a regular wards method, which is completely different. The difference between the two is the wards method. So not D2 uses squared Euclidean distance, and this ward D2 uses just the square root of the distances. And the default for this, I believe, is complete linkage. So if you want to do something different, you have to make sure to specify in method what linkage method you want to use. So we can plot that by just calling plot, and then we get something that looks like this. So again, as I said before, right, there looks to be some cohesion towards the bottom is essentially what we want. They're not as small as I would like in terms of the vertical distance, but it's okay. And I think it's, well, maybe it's not so clear. Where would you guys cut this dendrogram? Yeah, so you could cut it here. I think that's reasonable. I would probably cut it here. I don't know. But again, you can see how subjective it is. But there are some, you can see how subjective it is. But what I want to talk to you about is kind of ways to determine this more objectively. So there's 3 types of methods that we can use to determine the optimal number of clusters in our data set. Jamie talked about this within sum of squares variance and minimizing it. That is the elbow method, and it's very similar to the elbow method that we use for factor analysis, right? So there we are looking for eigenvalues or the particular factor that explained the most of the variance. Here we're looking for a factor that minimizes the within cluster sum of squares the most. There's also the silhouette method that is very popular, and that's just a measure of how good your clusters are, and it can range from -1 to 1. And there's 2 important parameters that I want to talk about, BI and AI. So AI is related to cohesion of the clusters. So it's the average distance between a data point and all the other data points within the cluster. We want this to be small. There's also BI, which is separability, which is a measure of the distance between I and other data points in a different cluster here. We want this to be large. So we want to have large separability and low cohesion. So we want this to be larger than this. and we want it to be close to 1. If we got a silhouette score close to -1, that would indicate that particular data points in a cluster should be in another cluster. It's not a good fit for the cluster that it's in. But just know that this is just a measure of the adequacy of your clusters and how good they cluster within. There's also the gap statistic that's relatively new. I think this was proposed in maybe 2001, 2002. This one uses the within cluster variation for different values of K. And this is compared to a null reference distribution. So a distribution where there are no clusters or there is no clusterings in that one. And what we want to do here is we want to maximize the gap statistic. And we want this to be as large as possible. If we have a large gap statistic, that suggests that our data set is clusterable, that there's clusters in it, and it's far away from this null distribution. So we can actually plot these things fairly easily. So there's a package called fviz and bclust that can do this for us. So what I'm doing here is I am calling the elbow method. So this is just the within sum of squares. I'm calling the silhouette method and then the gap statistic. And then we can put these all together and we would get something like this for our data. So what can we say about the number of clusters that are ideal here? It's not really clear, right? So if we use the elbow method, we might say maybe 2 clusters is where the elbow is. I don't know. The elbow method is not that good. Silhouette method, we say about 2. And what's great about this is that actually, at least for silhouette method and gap statistic, it basically has like an outlined line that tells you the number of clusters you need. This one says 2, and then the gap statistic says 5. So basically what we have is that 2 to 5 clusters would be adequate for our data. That's no good. Another method that's gaining in popularity is bootstrapping the hierarchical cluster. And Easy Stats has a function called nclusters, hclust, that will basically run your hierarchical cluster and then output a dendrogram with the number of clusters that it deems sufficient for your data. So there's 3 numbers that we want to be aware of. One is the edge number, which is just the extracted cluster. So was it extracted first to n? Then we also have red, which is approximate unbiased p-value. And then we have BP, which is just the bootstrapped p-value. And what it does here is it finds clusters that are about 95 to 100. So we want the scores on the left-hand side to at least be close to 100. And if it's 95 and above, that is approximately p.05. So what this is doing is finding those high p-values and then using that to determine the number of clusters here. So this is suggesting that we need 2 clusters here. And I like this because it's objective and we can assign some significance to those clusters to see if they're meaningful or not. If we just do a hierarchical cluster analysis, again, it's going to return clusters, right? So this gives us a way to objectively test whether those clusters are actually meaningful in some way. So I like this method. Yeah.
How is the p-value calculated?
So basically, when it's forming clusters, it does it like, I don't know, 500 times, and then it counts how many times that was selected as a cluster to merge. Yeah. And then I want to say that, so you can set the hclust method. So here we're doing the wards and the iterations are at 500. I probably would bump that up to maybe 5,000 or 10,000, but it will take a long, long time to run. So be aware of that if you wanted to use something like this. So the bootstrapped hierarchical cluster said that there's 2 clusters. So we can use this fviz dend to visualize this cluster analysis, which I think is pretty nice. So basically it has these boxes around the 2 clusters and they're color coded. So we have a red cluster and we have a blue cluster here. I think Colleen was talking about this. So this is a circular way to kind of visually represent the dendrogram, which I kind of like. I guess it could be made a little bit bigger. So some of the labels are actually shown fully, but yeah, I think that this is a nice way to visualize something like this because it could be kind of hard to visualize something like this, where this is kind of a little bit more straightforward, I think. So we can use the silhouette method as a goodness of fit measure. Running this fviz silhouette function will return this nice graph here. And this is usually reported when you're doing hierarchical clustering. So what we have here is if we have a data set with only one cluster, the average silhouette width, so how good the cluster is 0.2. With two clusters, it's a little bit better at 0.42. Ideally, you'd want your silhouette method to be over 0.5. I don't know what this dotted line is here, but yeah, we'd want something at least 50% or higher for adequate clustering. And you can try adding more clusters to this, and I didn't see really any gain in the silhouette width. So going with the bootstrapping here. So once you decide on the number of clusters, we need to assign them a label or a name. So for this one right here, the red cluster, I am just calling that the English cluster because it seems like all of the English tokens are clustered together in this one. And then cluster 2 would be a non-English cluster. So that's how you can partition this and assign it a label. If I could see maybe if we got some bilinguals or multilingual folks, we might have more clusters. And again, as Branson said, you could probably cut this lower at 4 clusters, and the actual groups that it creates do make sense as well. So the PI that I was working with on this, I came to her and I said, it looks like 2 clusters adequately explain the data. And she's like, no, I like 3 clusters better. So she went with 3 clusters. So again, it should be guided by experience. It should be guided by theory. But I do like the objective way to get at what clusters there are in the actual data. So some pros and cons of the hierarchical cluster. So pros, it shows all possible connections between your variables, which I think is useful. It helps us better understand the data. I like that you don't have to preset any cluster values. So I don't need to say fit 3 clusters, 4 clusters. We let the data speak for itself, which I like. But the cons are it's very subjective, as we've seen, and also scalability. So if we have lots and lots of data, it's going to take a really long time to build that dendrogram. And if we also use things like bootstrapping, it's going to take even longer. So now I want to move into k-means clustering. Do you guys have any questions about hierarchical clustering? Some burning questions? It's pretty straightforward. So Jamie did a nice job of explaining k-means clustering. So I'll just use this GIF here that explains it, right? So we have to pre-specify how many clusters we want. In this particular example, it's 3. And what we do is we figure out where what clusters the points cluster with the closest. So I use this pen here. So if we take this data point right here, we basically calculate the distance from this data point to this cluster center, and then to this cluster center, and this cluster center. And we can see here that this particular data point is closest to this red cluster here, right? So that's what we would do. Then in clustering, we recalculate the means for those clusters, right? So now it's in the middle of this group. And then we keep doing this until we have convergence. And when I say convergence, I mean that the cluster membership doesn't change or only changes a tiny amount. And that's the basic idea behind k-means clustering. So to kind of see k-means in action, we're going to use an oldie but goodie data set, and that's the IRIS data set. I scoured the internet for simple k-means data sets, and I just couldn't find any ones that were good. So I have to use the IRIS data set. But I do have a good data set for Wednesday's class, though, so I didn't want to burn that here. So the IRIS data set, again, is old, and it's kind of cheating because it already lists the labels. So it has 3 distant type of iris flowers, and it labels what those are, right? So the iris setosa, the versicolor, and the virginica. And in this data set, we have the petal width and length and the sepal width and length. So that's what we're going to use to see if we can categorize these into 3 groups. So we can read in the data. I believe it's in base, so you don't need to download any packages. And then what we're going to do is also standardize this data set because they're on different metrics. So we can use the data wizard function standardize to do that. or we can just use the scale function in base R. And it's also a good idea to just look at the data as well. So if we look at sepal length and width, there doesn't look to be kind of any distinctive groups that kind of appear here. They seem to kind of overlap with one another. But when we look at the petal length and width, there does seem to be some separation here, where the Cetissa species looks to have shorter length and width for petals. But there's not a lot of separability here. So we might not be able to actually pick out 3 clusters. So we'll try it out and see. So there's a couple different ways that we can perform k-means clustering. One is using the k-means function, which is in the stats package. And again, I don't think you need to download any packages for that. And here, what we want to do is put in our scale data, and then we also want to specify the number of clusters we want. So here, we're just going to say 3 clusters, right? So there's 3 labels in the data set. Let's use 3 clusters to start off with. So if we look at the summary output, it has basically the clusters and the sizes of those clusters, so how many observations per cluster. It gives you cluster means, and then it also gives you the actual assignment of the group to the data. So if it was in 1 or 2 or 3, that's all labeled in this summary report here. You also get within cluster sum of squares, and then some other types of statistics here. The other way that we can run the k-means clustering is with cluster analysis, and this is from EasyStats. And again, we put in our iris scale data, we specify the number of clusters we want, and then we're going to use k-means. And what I like about this one is that you can feed it into plot, and it produces a pretty nice plot here. And we can kind of see that there are 3 clusters here. This one stands out, right? So this is the Cetissa, I think. And then we have the green and blue, but it seems like there's some overlap between those 2. So is 3 clusters the optimal number of clusters? Well, we can test that empirically, right? This is a function to visualize your clusters. So fviz cluster, I think, is nice. And it kind of outputs the clusters with these kind of trapezoids. You can also do different shapes if you want. All right, so similarly to hierarchical clustering, we can use the elbow method, the silhouette method, and the gap statistic to check to see what the optimal number of clusters are. So looking at these methods, so elbow method, silhouette method, and gap statistic, I think that there is a clear consensus here on the number of clusters we should have. And that looks to be 2, right? So our elbow method, it seems like the elbow of this is at 2. For the silhouette length, or the silhouette width, it's about 2. And then for the gap statistic, it says 2. So maybe we can't have 3 clusters in our data set, or it's not the optimal number. It seems like 2 might be the optimal number. So what we can do is, again, we can fit this cluster analysis again with k-means, and we can set it to 2. And we get something like this. But similarly to the factor analysis and factors function from EasyStats, we can do this with n clusters, and it does it automatically with this cluster analysis function. But basically, it uses a consensus method to determine how many clusters we should have in our data. So when we run that, it says that there's 2 clusters, and that's supported by 15 out of the 29 methods. So I like this way better because it's a little bit more objective. And then we can plot it, and this is the data with just 2 clusters here. Again, the versicolor and the virginica have been merged together, and they're not separate anymore. And then the cluster 1 would be versicolor, and then cluster 2 here would be the Cetissa or virginica clusters. This is a silhouette score that tells us just how good the cluster is. So we see with 2 clusters, the width is about 0.53, which is okay. It's not 0. For 1 cluster, it's about 0.68. Not sure if we should even have 1 cluster instead of 2 clusters. But I'm kind of curious, though, too, if we use different methods, if it'll recover the 3 species, or if all of them just say that there's 3 species here. But if we didn't have the labels, we'd probably go with 2 species or 2 clusters. So that's interesting. So also when you do cluster analysis, again, we get these labels for our data now. So we get cluster 1 and 2. We can actually put that back into our data set and perform additional analyses on that. And that's what I have displayed here, where we have this predict function. So this works for cluster analysis that's been done by EasyStats. So you can just call this predict, and then you can add that to your data frame. I think K-means also has something like that, where you can just take the actual cluster assignment and then append it to your actual data set. So then you can do some additional statistical analyses. So pros and cons of K-means. So pros, it's simple and fast, and I think it's pretty intuitive. Some cons of K-means that Jamie pointed out, it's really sensitive to outliers. The number of clusters can change depending on the order of the data. So if you could do this again, and you might get slightly different cluster assignments. And it also assumes a spherical density, which might not be observed by all of the clusters, right? So spherical density here is that it's fitting it spherically. So that means that the distance are all the same between the data points in the center cluster, which probably is not a very good assumption. But there are other types of clustering methods like dbScan and K-metoids that are very robust to outliers and also this spherical density one. So you could try fitting something like that. But, all right. And special thanks to Chelsea, since I stole most of her slides. So not all of them, some of them. So I just really like her visualization. So are there any questions about K-means and or hierarchical clustering? Again, very quick. I think it's pretty straightforward, but just wanted to give you guys an idea of how to do this in R. Yeah, Cindy.
The difference between this and like factor analysis?
Yeah, so factor analysis is basically trying to maximize the variance, right? And this one is just trying to minimize the within cluster variance. So different aims. Because again, we want data points within clusters to be as similar as possible from other clusters. And PCA or factor analysis is just trying to maximize that variance and explain that in the data set.
In PCA is like you don't know what measurements in your data are actually informative. Like here would be like double length versus like simple length, and you're like, and these actually tells me the most about my data, like differentiates the groups. Clustering would be like how many groups fit in a database of the measurements. It doesn't tell you which measurements to use.
Yeah. Yeah. Especially like with K-means.
I was just gonna say that I also learned how it was explained as like PCA. You can think of it as like a feature reduction.
Yeah.
So like what Brad was saying, trying to figure out what is the most important features. So like clustering, you are basically using all the features. Yeah, to build up
But similar, but different, slightly different. Again, it's just how we're partitioning the variance. Yeah. So again, you can see how we had all this data set with the tokens, right? With the speech tokens, and we were able to condense them down to just 2 clusters. So again, dimensionality reduction, but we can use that to do other analyses.
I'm kind of wondering how you would use clustering to answer a question that you have, like to test different hypotheses. Because I mean, I guess we have this like goodness of fit measure,
Yeah.
and you can like fit different clusters to test.
Yeah.
It seems like a.
Are you talking about like statistical, like test the differences statistically?
In a way, I just like wondering, like, I guess you have this question, like, can people sort speech by accent?
Yeah.
For instance, if you can cluster, then I guess that supports it.
Yeah.
It doesn't. It seems like a pretty indirect way to like pit hypotheses against each other. It seems like pretty exploratory.
Yeah, and I think that's why the creation of the clusters are important to do like further analyses on them, to test that. So I think that this would be like the first step in something to see kind of what's grouping together and what potential clusters do I have, and then further testing that. I wouldn't say like, we just did this cluster analysis and that's it. Like, these are the clusters. I think that there needs to be some more follow-up and additional hypotheses tested. But if you have lots and lots of data and you kind of want to see what groups pop out, I think this is a good first step for sure.
I've seen clustering use a lot of like clinical studies, where you got,
Yeah.
the diagnosis, very broad, and you try to figure out subgroups.
Yeah. Yep. That's a big use of clustering. Yep.
I think it's really, it sounds like it's really good for like visualization of different groups. It's like, really useful.
Yeah.
So, like, when you measure along these different, like these dimensions, you can like really see that they form
Yeah.
types.
Yep.
Imagine an example. If you really want to show like, these are like two different groups under the same diagnosis. You can really see that visually.
And that would be definitely very useful. Because then you could also group your patients, right, as whatever, depressed, not depressed. Or you can actually look at the hierarchical clustering between like different types of patients. Do they group things differently? So Wednesday, I have a data set that looks at that. So it is a patient who has anosmia, so can't smell. So it's comparing that particular patient with just normal samples to see if the clustering is different between the two. So that's an interesting application, I think, of hierarchical clustering. Or you can group Donald Trump's tweets. Lots of cool things to do here.
Show that he's truly built it.
Yep. Yeah. Yeah, no, is there any other questions? Do any of you guys have different applications of clustering that you see?
Some papers that do emotional expressions.
Okay.
To see if it's like basic 6 or valence.
Yeah. So what usually, like, what is usually born out from that? Is it the basic 6 or no? Okay. Yeah. How many clusters usually are born out from that?
That really depends on how many different types of screen you use.
Oh, okay.
Sometimes they use-
Interesting.
More about how you ask,
Yeah.
Oh, yeah.
All those things.
What would you say, Jim?
like how do you work?
Questions.
Oh,
Interesting.
at least if I can get
So this is all I have for today. So if you want to leave, you can. If you want to stick around, you can. I know Killian and Nicole are raring to give their talks. So
You're just saying it.
They all, I think it might be.
They're in person. I was on Zoom.
Yeah, Casey Connors be like right after.
Oh, right after, okay, good. We have.
Well, is it feedback? Yeah, they don't share.
Let's go through all your things.
There's the slash. Yeah, like, I just feel like we're saying we don't know. You've done all this other stuff. I'm like, this is the one time.
You know what I mean?
No, I guess it's your time to see.
Yeah.